and welcome. What I'm going to do today is I'm going to be going through this overview. So this is an electricity overview. It has a little bit of everything, and I'm going to go through how I do it and important things to look out for in questions. So I'm going to start with a couple of multiple choice, and this first section is basically just doing some really basic looking at how circuits are done. Okay, so this is actually quite an interesting circuit. It says a cell that has an EMF of 2 volts. Now, this whole first part is really important because what this is implying is that there is internal resistance. Okay, so what it's actually saying is that there is no thing that says there's negligible internal resistance, and I've pointed that out before. If they don't say that, it implies that there is an internal resistor. So what actually this circuit should look like is there should be a little resistor here, and then there should be a nice little cell like this. So the EMF is 2 volts. And when the variable resistor is 4 ohms, so when this is 4 ohms, if I had a voltmeter here, the voltmeter has 1 volt across it. They're now asking if it is 12 ohms, how much voltage will be across it. So we're trying to find little r first because we know there must be an internal resistor. So I'm going to be using this first. So if we actually look at this circuit, I can work out we're going to call the circuit 1. So on circuit 1, I know that over the 4 ohm resistor, there is 1 volt. So the current in that circuit is going to be 1 divided by 4, so that's 0.25 amps. So I know that in this circuit, there's 0.25 amps flowing. I know on the internal resistor, there is 1 volt. And I know that through Kirchhoff's law, because this is 2 volts, and I've got 1 volt across here, so I must have lost 1 volt across this one here. So I know V equals I little r. So 1 equals 0.25 little r. So little r is also going to be 4 ohms. So if I was to redraw the circuit for this section here, I would have this here. I'd have a 4 ohm resistor here. I'd have a 12 ohm resistor here. And I'm trying to work out how much potential would be across the terminals of the cell if this was my situation. Okay, so I'm just going to minimize this a little bit so I can draw a little bit more. So in this circuit, circuit 2, my total resistance is 16 ohms. My total voltage is 2 volts. So I can work out my current. So that's going to be 2 divided by 16. So 2 divided by 16, so 0.125 amps. And then, of course, I can then work out how much terminal potential there was. And terminal potential is how much potential is given to the rest of the circuit, which this 12 ohm resistor represents. So I know that the voltage over here, so the voltage over the 12 is going to be 0.125 times by 12. Oops, which is going to be 1.5 volts, which is going to be this one here. Okay, so this is actually quite an interesting question because the first thing you must realize is that it doesn't mention negligible internal resistance, which means there must be an internal resistor. And as you can see, I've sketched all over my diagram, and you're more than welcome to do that. So that's really, really useful for you to do. Okay, so this is that's an internal resistance question, but I'm using Ohm's law, and you'll find this a lot, that when I'm actually doing all my circuitry stuff, I tend to very, very, very rarely use sort of the equations that are in the data sheet. I tend to use Ohm's law and Kirchhoff's laws a lot to help me, and I draw all over my circuits. So I'm just going to press enter, and I'm going to try and move this down, but it's not happy. So let's just move this down. So So I'm going on to question 2, which is actually more of a pure sort of circuit analysis question here. So what I've got here is I've got 4 lamps, A, B, C, and D in the circuit shown in figure 1. So we've got a lovely circuit here. So A and B are in series and C and D are in series, and they're both in parallel with each other. The table shows the operating conditions when of the lamps when they're at their normal brightness. So when they're at their normal brightness, A and C have an operating voltage of 6 volts. Whoops. And B and C have an operating voltage of 3.5 volts. The student observes 2 of the lamps are not at that normal brightness. Assume that any changes in resistance are negligible. So what they're saying here in this section, here, 2 seconds. There you go. There we go. Sorry, my pen sort of ran out here. So the table shows the operating conditions where they're at normal brightness. The student observes that 2 of the lamps are at their normal brightness, and assume any changes in the resistance are negligible. What this section is saying, okay, is that they're basically the same resistance no matter what. So a lamp, just to remind you, has IV characteristic like this, that it changes over time. So what they're saying is that the resistance is constant no matter if I'm not at its maximum power or not. Okay. Now the reason that I know that only 2 of them will be at their normal brightness is all to do with the fact that if you look at Kirchhoff's law, if I went round in one loop, so I can go around in this loop here, or I could go around in this loop here, so I can go up here, I can go up in this loop here, I know that they're going to be sharing only 9 volts. And if you think about it, I will go through either A and B, or I'll go through C and D, and their operating voltages are 6 and 3.5. So technically, if they were both working at their normal brightness, I would have a total of 9.5 volts required over each one. And that is more than I'm actually getting supplied. So this means that some of the lamps are not going to be asked at normal brightness. And we're going to find out which ones they are. And the biggest hint you had was this section here. Assume that any changes in resistance are negligible. So they're giving you a hint by mentioning resistance. So what I'm actually going to use is this information to work out what their resistances normally are. So I've got A and C. Okay, so power is V squared over R. So R is V squared over the power. I'm going to work out what the power is. So I've got 6 squared over 6, so I've got 6 ohms. So the resistance of A and C are 6 ohms. So these are 6 ohms. And B and D, I've got power equals V squared over R, so R equals V squared over P. So it's going to be 3.5 squared over 4.1, and that is approximately about 3 ohms. Okay. So I know that the resistance of these lamps are going to be 6 ohms and 3 ohms. And what I'm going to do now is I'm actually going to redraw the circuit. I'm going to draw it down here. So I've got 9 volts, and I've got a resistor here, a resistor here, a resistor here, a resistor here. Comes down like that. This is A, this is C, this is B, and this is D. So I know that if I actually look at these things here, I've got a 6 ohm resistor and a 3 ohm resistor. And here I have a 6 ohm resistor and a 3 ohm resistor. So I know that going on each branch here, I have 9 ohms. And I know that each branch will also get 9 volts. So what I can do is I can work out how much current we'll be getting down each branch here. So B of the branch equals I times by R. So I've got 9 equals I times 9. So that's going to be I is 1 amp. So I know that each branch is going to get 1 amp. And then I can work out on each one how much voltage they're going to get. So it doesn't really matter. I can look at each branch because the branches are identical. Let's just look at this branch here. So A is going to be, the voltage on A is going to be 6 times by 1. So that's going to be 6 volts. And the voltage on B is going to be 3 times by 1, which is going to be 3 volts. So what this actually, if you look at, this is actually where it becomes really important, is that if you look at A is getting its operating voltage. B is not getting its operating voltage. Okay? So what this means here is that A, should not be writing in a highlighter, A is getting max voltage. So A is at normal brightness. Okay, so A is getting the maximum voltage, so A is getting the normal brightness. And as you can see, what I did here is I actually just literally looked through the circuit. So if I actually go through the mark scheme itself, you get 1 mark for trying to work out the resistance, okay? So you get 1 mark for doing the resistance calculations. Okay, 1 mark here is actually working out these voltages here, and 1 mark is for actually identifying that it's I do apologise, it's 2 lamps, so it's going to be C and A is getting the max voltage, so A, let me just delete that, C and A is getting the normal brightness. Okay, so this is actually quite a mean question because there's a lot of information going on here. But I kind of got cues from what the question were asking. So the fact that they're mentioning about resistance, I'm using that as sort of like, okay, they're talking about resistance. They're saying the resistance doesn't change when it goes down. You go, oh, okay. They give me power that I'll calculate the resistance. It's all about getting those cues from those actual things. And as you can see here, all I did was just redraw the circuit and label it here. Okay. So just move that back up here. Move that there. Okay, so this is now what's going to happen. So let's actually, this is exactly the same circuit. And so we know that this is 6 ohms, this is 6 ohms, this is 3 ohms, and this is 3 ohms. And we're told that we're going to connect another lamp across this, and this one here is also going to be 6 ohms because it's identical to A and C. Okay, and it's stuck between these 2 points here. Now, this is actually really, really cheeky, and this is the reason I put this question in here to get you thinking. If I looked at this position here, and if I looked at the electrons that would be flowing through here and through here, okay, electrons, when they move around circuits, are gravitated to things that are more positive or more negative, or more positive, say, are electrons. But here, if we actually did the maths, the electrons, as they would actually go around here, they would have lost the same amount of energy when they went through A and C. So they would have the same amount of charge, the same amount of potential left when they would leave, because of V equals IR, the electrons lose the same potential on A and C. So they go round, and at this point here, I'm going to call this X and I'm going to call this Y. So at X and Y, the potential is the same. So why would electrons even think about flowing between X and Y? The electric field, the charge, the thing they're attracted to is exactly the same at these points. There is no movement. They would have no desire to move between these 2 points. It would be kind of like if you imagine having some things here with exactly the same repulsion and attraction at the point. Why would they move between those points? They're not going to. What the electrons will do is just literally just carry around like this and completely ignore this X and Y junction. So this is actually a really, really mean question. Explain what the student would observe regarding the brightness of the lamps. refer to the potential difference of E in your answer. You can, what's actually really important is this is a 3-mark question. So it's 3 bullet points that you have to write. And the first thing it's saying here is explain what the student would observe regarding the brightness of the lamps. If you are unsure, because this is a really mean question, you can actually just have a guess. Would they get brighter? Would they get dimmer? And would they stay the same? The answer is, of course, as I've explained, they stay the same. Okay. All right. So they stay the same brightness. But if you're unsure, you could have a go. And the reason being is because E does not light up, taking no power or energy away. This is because there is no potential difference across E. Okay, so there is no actual potential difference across E. There is no way for the electrons would not flow through E because there is no potential difference at that point. A and C are going to take exactly the same amount of voltage. So when it gets to X and Y, there is no difference between those voltages, so no current would flow. So the current will not flow between X and Y, it'll just carry on straight through. Really, really mean question, has happened before, but it's to get you to think. But even if you are unsure, you could have a guess. Explain what the student would observe regarding the brightness of lamps. I'm having a go. I'm saying it would stay the same brightness. You get 1 mark for stating that. Okay. You get the next 2 marks here. So actually mentioning that the light doesn't turn on because there's no potential difference between E. Okay. What I'm doing is I'm explaining how this happens. It's a really mean question, but if you do see it and you're not 100% sure, have a go. Say, does it go up, go down, or stay the same brightness? Don't leave it blank. Do have a stab in the dark. Question C states the lamp B in figure 2, so it no longer conducts. So what happens is this lamp here breaks. Deduce the effect of the current in the battery. So let me actually just read all the circuit. So what we have now is I have my 9 volts. It comes up. I've got my resistor. This is my A. I've got my E. I've got my C. And of course, D here. And what's actually happened is this one here has broken. So it's big, no, it doesn't work. So actually what my circuit really looks like now is like this. I have got a resistor here. I've got 2 resistors here. And then I've got 1 resistor here. And we know that A, C, and E all have 6 ohms because they are the same resistor. And D is 3 ohms. Okay. So it says deduce the effect of the current in the battery. Okay, so again, you could have actually had a wild stab in the dark of this. This is a up, down. Does it go up? Does it go down? Does it stay the same? Okay, you could have had a guess in this one. And it says use calculations to support your answer. And this is where the other marks come from. So let's go into the figure 1 circuit. All right, so figure 1 circuit, you know from what we did before. We got here. You got figure 1 here. We know that there's going to be 2 amps in that circuit. Okay. In the figure 2 one, we're actually going to do a bit of maths on this one. So I'm going to work out the total resistance Okay, and first of all, we're going to work out this section here. Okay, and we're going to call this section Z. So it's going to be the resistance in section Z plus the resistance at D. So the resistance of Z is going to be 1 over, so the 1 over the resistance of Z is going to be 1 over 12 plus 1 over 6. So 1 over 12 plus 1 over 6 is 1 over 4. Okay, so the resistance of Z is going to be 4 ohms. So the total resistance is going to be 4 plus 7, jumped the gun, 4 plus 3, which is going to be 7 ohms. And so the voltage total equals the current total times the resistance total. So 9 equals I times by 7. I equals 9 over 7. So 9 divided by 7, which is 1.23 amps. So the current decreases. Okay, so how you actually get marks for this one is you actually get 1 mark for actually saying something. Does it go up? Does it go down? Okay, I get 1 mark for mentioning that the current in the first circuit was 2 amps, and the mark says it can actually come from part A. They're actually not expecting any marking or they're not expecting any calculation. You could have done it, but what they're doing here is they're making you look at that. They're looking for a calculation to find the current in the new circuit, and they're working out here. If it says here, if the circuit increases and the current decreases, no other marks, you can score 1 mark just for having a random stab in the dark. Now, this actual whole question is quite mean because it's using a lot of information that may not be visible to you. But one of the things I want you to make you aware is that drawing the circuit, looking for cues of what they're trying to give you information of that, have a stab in the dark. Go, cool. If this was a lamp, this was a circuits, what would it do? B is mean. I won't lie. B is a very mean question to get you to think. C is having redrawing the circuit is really important to visualize what's going on. But what I've shown you for B and C is that you could have had a stab in the dark, because by saying what would it do, would it go up, go down, or stay the same, having a stab in the dark is really, really, really useful. So in this one, for example, having a stab in the dark and going, cool, the current goes down, you can actually pick up marks that way. Okay, so I'm going to move on to now is question 3. And question 3 is a resistivity question. Okay, and what we're going to do here is talk about this. So this is actually a power cable. So we've got a steel power cable in aluminium. And if I was actually to draw this as a circuit, what it would look like is 6 rows. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. It's basically 7 pieces of cable that come together and do that. That's what it looks like. So resistance of a length of 1 kilometre of steel wire is 3.3. The resistance of a length of 1 kilometre of one aluminium wire is 1.1. The steel has a diameter of 7.4 millimetres. Calculate the resistivity of the steel. State an appropriate unit. Okay. So what we're going to do is we're going to use the information we've got here. And we're going to do, this is of steel. So this is the information we're after for steel. So there's 1 steel wire. I know the resistance is going to be 3.3 ohms. I know the diameter is 7.4 millimeters. So the radius is going to be 7.4 divided by 2. Whoops. So 3.7. There. And so we're going to use resistivity is RA over L. We can see it's a circle. So we know it's going to be 3.3 times by the pi r squared over the kilometre, because it's the information we know about. Putting it in there. So 3.3, so 3.7 times 10 to the minus 3 squared times by pi times by 3.3 and divided by 1 times 10 to the 3. We get an answer of 1.42 times 10 to the minus 7 ohm meters. Okay, so it's 1.42 times 10 to the minus 7 here. So mark-wise, you actually get one for calculating the area, one for the unit, and one for this here, and actually one for doing the sum there. Okay, so you actually can lose if you forgot to divide the if you forgot to convert, you'll lose both marks, but they will allow you if you accidentally use the diameter instead of the radius. Okay, so a really nice 4-mark question there for resistivity, and quite simple in terms of this. Now, this is an explain why only a small percentage of the total current in the passes through the steel wire. Okay, so this is a 3-mark question, and it's all to do with the diagram I have a look here. So it's all back to this diagram that I drew here. So I have 7 wires it could go down to. 6 of them have a resistance of 1.1, and 1 of them has a resistance of 3.3. So there's 2 factors why only a small amount of current goes down the steel wire. And the first one is that there is more paths of aluminium than steel for current to travel down. Oops. Okay, so there's more paths of aluminium to travel down with the circuit in parallel. So that's the first thing. You actually notice that there's 6 more paths for this to go down and that. So that's the first one. The second one is actually more to do with the information about what do you know about current and resistance. And the steel is 3.3 times more resistive than the aluminium. Okay, so it's actually the resistance. This is the second part of the thing, that you understand that the steel has more resistance than the aluminium. Okay, and current always takes the path of least resistance. Okay, so the steel is 3.3 times more resistive than aluminium. Okay, which means the aluminium takes 3.3 times more current than the steel. Okay, so the steel being more resistive means that the aluminium will take more current, and that's where the sort of other section is. So there's the first one is mentioning that there is genuinely more aluminium than steel, and the second and third mark are for realizing that because the steel is more resistive, that more current will go down the aluminium instead because of V equals IR. Okay, so this is all to do with V equals IR. Okay, so the potential difference, I'm just going to press enter and move this one down a little bit, move that back up. So just move this one down. So the potential difference across the length of the 1 kilometre wire is 75 volts. Calculate the power loss for a kilometre or length of the cable. So what I have here is I've got my 75 volt battery. I have my cable with my 1, 2, 3, 4, 5, 6, 7 cables. And I want to know how much voltage will be lost across here. So what is the voltage loss here? And so therefore, what's the power loss? Okay. So the potential difference across this, so I do apologise. I've got 75 volts here. So this is how much I know if I put a voltmeter across here, this is how much I've lost. And it wants to know how much power I've lost. So I know the resistance of this cable. So I have 6 times 1.1 ohm cables and 1 times 3.3 cables, and they're all in parallel with each other. So in essence, the resistance of this section, is going to be 1 over the total resistance. It's going to be 1 over 1.1 plus, and that's going to be 6 times, plus 1 over 3.3. So what that's going to be is 6 over 1.1 plus 1 over 3.3. Oops. So 6 over 1.1 plus 1 divided by 3.3. So my 1 over the resistance is going to be 5.75. So my resistance of this section is going to be 1 over that, which is 0.174 ohms. And you can do this a multitude of ways. You can use power equals V squared over R. So that's 75 squared over R. So 75 squared divided by that. So that's going to be, 32 kilowatts. 32 times 10 to the 3 watts. Okay. Doesn't seem right. V squared over R. No, that is right. Sorry, I'm looking at the answer, getting really confused. So that's how you could do it then. You could work out what the current was and use P equals IV, but you're actually going to lose quite a lot of this. So the way I answered this question is I went, okay, what does the circuit look like? And I actually draw the circuit. I actually drew what the circuit would look like here. And I knew it was all in parallel because you can see from the diagram before, it was like this line of cable and all the current is going down it. So I drew this here, and you've got one steel one surrounded by loads of aluminium ones here. And so what I did is I know there's 6 times this cable plus this. So they're all in parallel with each other. So I worked out what that resistance was. I used the power formula and I go up. Drawing the circuit is so useful. Especially when you're trying to make sure that you know what's going on. Okay, so question 4. Question 4 is another resistivity question. It's quite a straightforward one. The wire in an electric heater is 75 ohms. It's 9.5 meters long and has a cross-sectional area of this. Calculate the resistivity and give an appropriate unit. Nice 3 marks. So rho equals RA over L. So it's 75 times by 1.4 times 10 to the minus 7, all over 9.5. So 75 times by 4 times 10 to the minus 7, divided by 9.5. And that is going to be 3.16 times 10 to the minus 6 ohm meters. And you just make sure you do put them in to the actual question box here. If you do have a line, make sure it's in there. Okay. I want to double check because my answer does not make sense of this one. So cross-sectional area is 75 times by 1.4 times 10 to the minus 7 divided by 9.5. Yep, I can't actually use a calculator today. So deleting all of that up. I was looking at the units are right. So I must have accidentally put that. So the actual answer is 1.12 times 10 to the minus 6. And it's still ohm meters. Me being an absolute, not 1211. Again, I can't read my calculator. Really sorry. Oops, 11. Okay. So the marks actually come from the substitution, from the answer, and then 1 for the unit. And again, give an appropriate unit for your answer. You can just get away with just writing the units there. Okay. So, question 5. So again, another resistivity, but there's a bit of superconductors in here as well. So room temperature metal has a resistivity and a wire has a radius of 0.7 millimeters. Calculate the resistance of a 2.5 meters. So rho equals RA over L, R equals rho L over A. So I've got 4.5 times 10 to the minus 7 times by, it's a wire, so I'm going to use pi r squared. They will tell you if it's anything different from a circle. So pi times by 0.7 times 10 to the minus 3 squared all over 2.5. And that's going to be 4.5 times 10 to the minus 7 times by pi times by 0.7 times 10 to the minus 3 times 0.7 times 10 to the minus 3 divided by 2.5. 0.7 times 10 to the minus 3 squared times by pi times by 4.5 times 10 to the minus 7, and then times divided by 2.5. Oh, I've just realised what I've done. I do apologise. I've actually done the substitution of the formula wrong. I'm looking at it going, I'm getting a really small number, and that sounds really wrong. It's actually going to be rho L over A. So it was actually going to be 2.5 and then over pi times 0.7 times 10 to the minus 3 squared. Sorry, that was my fault. I do apologise. I'm not on the ball today. I do apologise for this one. So 2.5 divided by pi divided by 0.7 times 10 to the minus 3 divided by 0.7 times 10 to the minus 3. And again, answer of 0.73. Whew. I was looking again, the resistance seems way too small and it didn't make sense. This is actually a really important step. So me making that mistake is trying to identify to you that A, people can make mistakes even if they have taught this and have already passed their A-levels in physics and all that kind of thing, got degrees in engineering, and they can still make mistakes. And it's all to do with the way I knew I was having a mistake was the fact that my answer was way too small for my resistance. The sanity checking process is actually really, really important to go, wait a minute, this answer makes no sense. I haven't seen a resistance that small. And go, oh, okay, and then keep going back and double checking your answer. So it's really important that these skills of going, oh, wait a minute, are actually really useful. So this one, again, you get a mark for using this, a mark for the substitution, and a mark for the answer of 0.73 watts. The power dissipated in the length of wire when it carries out the current is 20 milliamps. Assume that the resistance in the wire is constant. Work out the power. So I'm looking for the power dissipated in the wire. So P equals I squared R. So I've got 20 times 10 to the minus 3 times by 0.73. I'm going to get 0.146. Okay. Times 20 times 10 to the minus 3. I'm going to get, I do apologise, 2.92. Watts. Okay, so 2.92 times 10 to the minus 4. Okay, now the answer actually says 2.96 and it's all to do with error carried forward, so it all depends on your rounding all the way through. So there's a lot of, you get 1 mark here, so it's a 2-mark question. You get 1 mark for actually doing the formula and 1 mark for the answer with an error carried forward. So I use 0.73, which means that as we go forward, my answer is not quite what the mark scheme is, which is 2.96, but because of what numbers I've used and I've shown my working, and this is why showing working is so important, so the examiner can see exactly what numbers you are using. Now, this is actually quite interesting because this question here is a superconductors question, but it's the graph, which is the same as the graph you would expect, but they're trying to throw you off. So the temperature becomes, because superconducting, as it's called, draw a sketch graph on the axis below to show how the resistivity of the wire would vary with the temperature, as it's called, from a temperature of 0. Okay, so this is room temperature and this is 0 in Kelvin, and this they're putting resistivity. So the graph you normally get taught is resistance and temperature, and you get taught the graph like that. But what they're doing is they've put resistivity, and they're only doing it to throw you because resistance is proportional to resistivity as long as the area divided by length is constant. Okay, and they're just saying it's this Y. So they're really getting you to think about the relationship between resistivity and resistance. And they're saying for this wire. So they're assuming that you should realize that the area over the length is constant. So technically, it's exactly the same graph as usual. And it's worth 3 marks, okay? So what it is here is you get 3 marks for the 1 mark for having that, 1 mark for a knee jerk nearer the bottom. So this is near, so the bottom, around about over halfway. And then you get 1 mark for this section here. But it's a really cheeky question because they're trying to throw you with resistivity. And so you might start questioning, oh, is that correct? But it is, if you actually think about what the question is saying. So it's the fact that it's saying this wire becomes superconducting. There's the wire. It's all about this wire. So A over L is constant. It's really cheeky. Okay. I picked these questions specifically because they're using all the formula but being a bit tough. Explain why explain here why the efficiency of electrical power lines is improved when replaced with superconducting wires. Standard response. Superconductors have 0 resistance at the critical temperature. Therefore, 0 power wasted. Okay, so 0 power wasted. So efficiency is 100%. Okay, so basically the mark scheme says with no resistance there can be no power lost. I'm saying the same thing. Superconductors have 0 resistance, therefore there is no power wasted. 1 mark, quite a nice standard question. Okay, so this is actually quite, again, I'm just using sort of tricky questions and sort of showing you the kind of things the exam board can throw at you. So we've got question 6 and question 7. 7's a multiple choice, but I'm going to be doing this question 6. So this is actually a question from a paper 2. All right. It's quite a mean question again, and I'm showing you these mean questions. So the engineer wants to use solar cells to provide energy for a filament lamp and a road sign. The engineer first investigates the EMF and internal resistance. So this is actually quite important. They've highlighted that this is a circuit with internal resistance. The engineer determines how the potential difference across cells refers to the current, and the results are shown in figure 1. Explain how the engineer would use the graph to explain how the engineer uses the graph to obtain the values for this. So the engineer has said that the EMF is 0.7 and the internal resistance is 0.8. So this is a stereotypical thing. It's quite basic. You've got a straight line graph and they're asking you how you can use the graph to get it. So if it's a straight line graph, it's normally something to do with the intercept and the gradient. So what we've got here is I've got PD so I've got y equals mx plus c. I've got PD on here and I've got gradient on here. Okay, so I'm trying to find an equation that has all this information here. So what we could do is mentioned internal resistance. We're going to go to the internal resistance formula. So I've got that equals V plus IR. So V equals EMF minus IR. And if I was to put that into here, I would have minus R here, and I would have EMF here. So explain how the engineer uses this to find the internal resistance in the EMF. The EMF is the intercept on the y-axis, and the internal resistance R. So you can write the full title, internal resistance equals the gradient. Okay. So literally 1 and 1 mark there. All right. They may be more specific and more specific. They might want the magnitude of the gradient due to the fact that it is, of course, it's a negative gradient. But again, if they ever ask you how to use the graph to find something and it's a straight line graph, bet your bottom dollar, okay, it's all to do with the intercept and the gradient. So in any practical sense, any practical paper you can think of, if you see a straight line graph and the question asks, how do you use the graph? It's all to do with intercepts and gradients. To operate effectively, the lamp needs a minimum of 75 milliamps. The current, at this current, the resistance of the filament lamp is 6 ohms. The engineer proposed to try the two circuits shown in Figure 2 and Figure 3. Deduce using calculations whether the circuits in Figure 2 and Figure 3 are suitable for this circuit. Oh, this is, like I said, this is a second year paper. So what it needs is this road sign here is 6 ohms, and it requires a current of 75 milliamps. So to work, it requires 75 milliamps. Okay, so you can actually work out the resistance of it, actually how much voltage it needs. So the voltage that it requires is going to be 6 times 75. Not 7.5, I'm just going to leave that. 75 times 10 to the minus 3. So 75 times 10 to the minus 3 times by 6 is going to need 0.45 volts. Okay. So that's what it's going to need in each case. So it needs that much voltage. I did it again. 75 milliamps. So that's how much voltage it requires to do over it. So that's how much voltage needs to be supplied by this actual thing here. So if we actually look at the cell for Figure 2, so for Figure 2, so it requires 0.45 volts to work. Okay. If we look at the Figure 2 situation, we've got one battery, okay, and we can go up to this graph. So the beauty of this one is we can actually look at the graph and look at this information. So I am looking at 0.45 volts of terminal PD, and that's really important to realize that this one is the terminal PD. So this is the one that goes to the circuit. Okay, so I'm going to look when it's 0.45. I'm going to go across here. I'm going to go down, and I'm going to see I'm only going to be supplied with 30 milliamps. So in the situation in Figure 2, if there is 0.45 volts of terminal, that is 30 milliamps provided by the cell, which is not enough. Okay, if I had any more current flowing through this, the internal resistor here would take more of that away. So if there was more current flowing, if I go up here, if there was more current, I actually get less terminal PD. So Figure 2, so deducing whether Figures 2 and 3 are suitable. So Figure 2 is not suitable because at 0.45 volts of terminal PD, there is not enough current supplied. Okay, so if I wanted enough voltage to be supplied, I'm not getting enough current, so I'm not going to get enough power. Okay. So by the way, this mark scheme, there are many different ways of doing it. And the method I'm doing is actually the middle one, where I've worked out how much I really need and I'm seeing if it is possible. Okay. So Figure 1 isn't going to work. So let's actually look at Figure 3. So what I'm going to do is I'm just going to come down here. I'm going to press enter. I'm going to actually draw Figure 3 here. So I've got my light, which I'm going to draw as a lamp. and I've got figure 3 has a cell with an internal resistor, has another cell with internal resistor, and it has another cell with internal resistor, and that all goes down to here. So what actually happens is my current goes through, it splits up, and it comes through. So what's actually going to happen is in my actual thing here, I can actually gain more potential. Okay, so the EMF of each cell is 0.7 volts. We were told that. So I'm going to get 0.7, 0.7, and 0.7. So in any loop that I could take, so if I just go down and change my color, so my electrons could take this loop round, or they could take this loop round. In each route, so the maximum EMF is going to be 1.4 volts, which is more than I actually require to get this thing working. But my internal resistor is going to take potential away each time. Okay, so the internal resistor will take voltage away. But what's actually more interesting is how much the current goes down. So these two here are actually going to take away much less than this. Okay, so let's say I needed 75 milliamps. Remember, I need 75 milliamps. I'm just going to press enter on here. I'm just going to move this down a little bit. So I need 75 milliamps in the circuit. So this is 75 milliamps. So as it goes through here, it's going to split up, and 75 divided by 2 is 37.5. So I've got 37.5 here milliamps, and I've got 37.5 milliamps here. Remember, if I go right back up, this is the things with second year questions. They like making you go back and forth. So I know the internal resistance is 8 ohms. So what I'm going to do is actually work out how much voltage is going to be left as it goes round. Okay, so if we think about it, I've got my EMF, which equals 1.4 volts. And that my EMF is going to equal the voltage on the resistor, the first one, so resistor 1, plus the voltage on the internal resistor 2, and plus the lamp. Okay, so it's the voltage on the lamp. So let's work this out. So I've got 1.4 equals 8 times 37.5 plus 8 times 75, times 10 to the minus 3, times 10 to the minus 3, plus the voltage on the lamp. So let's see if we've actually got enough voltage left on this lamp. So we're going to need the magical 0.45 volts. So I've got 8 times 37.5 times 10 to the minus 3. So I've got 1.4 equals 0.3 plus then 8 times 75 times 10 to the minus 3, 0.6 plus the voltage on the lamp. So the voltage on the lamp is going to be 1.4 minus 0.9. I get 0.5 volts. Whew. So figure 3 works. So what this question is actually doing is getting you to think about how the circuit is this. And it is a really mean question. And this is why it's a paper 2 question in a second year format. It's not, it's a paper 1 question, but it's a second year question, not an AS question. But what it's getting you to do is to use your knowledge of Ohm's law and Kirchhoff's law and internal resistance to work out what's happening. And where you can pick up marks is quite effective. So for example, if you knew that the current had to be 75 milliamps and there's 6, you actually get 1 mark for literally working out what voltage you are required. Okay. You then get 1 mark, so that this itself, working out the voltage that was required, was 1 mark in itself. The second mark was for realizing that figure 2 couldn't do it. So when I looked at the graph, I went to 0.45 and I went, no, I'm not going to get enough current from 1 battery. So actually realizing that I wasn't going to get enough with the first one gave me the second mark. And that's 50% of the marks, just for realizing that figure 2 couldn't work, because to have enough voltage, I'm not getting enough current. And to have enough current, I wasn't going to get enough voltage. So if I went to 75 minutes, I'm not getting enough voltage. So you can pick up 50% of the marks literally just by working that out. The other 50% of the marks are harder, and they're trying to get you to think about how the flow of the circuit goes. So what I've shown you here is what I would have done. I drew the circuit out, and I would have gone, cool, so my electrons can go in this path and pick up 1.4 ohms, so that each time they're going to pick up this 1.4 ohms, I want to see that if I had 75 milliamps, would I have enough voltage left? So EMF of each cell is 0.7, so the maximum EMF I could have collected was 1.4 volts. I need 75 milliamps in the circuit. Let's see if I get enough voltage. So what I literally did was went through and see if there was enough voltage left on my lamp, and indeed I did have enough voltage. It's a mean question, I won't lie, but it is a paper 2 question. It is a paper second year question. But you could have picked up 50% of the marks by just basically going, cool, V equals IR. I haven't used it yet. Let's use it. V equals IR. How much voltage do I need? 0.45 volts. Go to your graph. Oh, wait a minute, I'm not going to get enough current, or I'm not going to get enough voltage. That would have given you 50% of the marks straight off the bat. The solar cell here converts solar energy to useful energy, the total efficiency of 4%. The solar cell used by the engineer has a total cell of 32 centimeters squared. Calculate the minimum intensity in watts per meter squared of the sunlight to create this much current. So the amount of power I'm going to need, so the needing power is, of course, 0.45 times by, sorry, it's actually been a bit more nicer. I'm not going to use that. I'm going to use this information here. So I've got I squared R, so 75 times 10 to the minus 3 squared times by 6, and that gives me the power I actually need. So 75 times 10 to the minus 3 squared times by 6, and that gives me the power I actually need, which is 0.03375 watts. So that is what I need, and that is 4% of what I got, okay? So this is 4% of what I got, so 100% of what I was given. So divide that by 4, times that by 100. I was given 0.84 watts per 32 centimeters squared. Okay, so that's how many watts I was given for 32 centimeters squared. Now I want to find for 1 meter squared. So first of all, I'm going to have to convert that into meters squared. So it's going to be 0.84 per, so 32 divided by 100 again, because it's squared, per 3.2 times 10 to the minus 3 meters squared. And so per meter squared, I'm going to divide 0.84 divided by that. So 0.84 divided by 3.2 times 10 to the minus 3 will give it to me in meters squared. So that's 262.5. So 262.5. So it implies that this is what I've worked out. This is a 3-mark question. You actually got 1 mark working out how much power you were given. You worked out how much power was sort of at the maximum, how much power in total that I had. Okay. And then you got 1 mark here for actually converting it into how much power that would be in a 1 meter square block. Okay, so I knew how much power I needed, So that was my 4%. I worked out how much I had on my 32 centimeters squared, and then I worked out how much it would be in a meter, and that was 3 marks in total. So what we're going to do is I'm going to put this up here. We're going to do the last question, which is question 7, which is a multiple choice question. So this is, again, back onto that cell kind of thing. 3 cells have an EMF of 1.5 and internal resistance of 6. Which combinations of these cells would deliver a total of 1.5 with a maximum current of 7.5 amps? So this one here, let's have a look here. So they're all in nice and series. So the total EMF is going to be 4.5 volts. Okay. And what's actually going to happen here is I've got 4.5 here. So I want a total EMF. Or a total EMF of 1.5 and an internal resistance of 6. So I'm just going, cool. So what's going to happen here, the maximum current is 7.5 amps. So let's actually have 7.5 going through here. So 7.5, so in this one, I've got 4.5 because they're all in series. So each time the electrons go around, it's going to pick up 1.5, 1.5, 1.5, so 1.5, 3, 4.5. I've got 7.5 amps here. So every time it goes through a resistor, it's going to lose 3 times 7.5 times by 0.6. So 7.5 times by 0.6 is 4.5 times by 7.5 times by 0.6 times by 3. So technically, in this one, it's going to lose 13.2 volts. So this one can't work because I'm only getting supply 4.5, and technically, if I had 7.5 amps going through it, I'm going to lose 13.2, so it ain't going to work. This one physically can't work. Can't work at all because of this bit here. It's the wrong way around. So let's look at this one here. Let's go down. So this one, they're all the right way around, so that's good. So I'm going to get a maximum EMF of here. So each cell has, I'm going to get a maximum EMF of 3 volts. So what's actually going to happen is we've got 7.5 going through here, and then as it goes through here, it's going to be 3.75, and that's going to be 3.75. So the voltage lost is going to be 7.5 times by 0.6, so 4.5, and 3.75 times by 0.6, which is 2.25. Which is going to be 6.75 volts. So even though, which can't work. So I'm not going to get my maximum current in this one at all. So let's actually look down at the one that it is correct, which is D. So I've got 7.5 amps going through. So it's going to go through each of those. 7.5 divided by 3 is going to be 2.5 going through each one. So for each branch, we're going to get 2.5 amps. So my EMF is going to be 1.5, which is what I'm after, that maximum EMF of 1.5. And to be honest, it was quite obvious that this was the answer. I'm just proving it why. And then if I actually look at the lost voltage here, I've got 0.6 times by 2.5. So 2.5 times by 0.6 is going to be 1.56. Okay, so what's actually going to happen here, the maximum current of which would deliver a total EMF at a maximum current of 0.75. So this one here could do it quite easily. You've got all that. So the answer, the only one that physically could do it is D. Okay. So the internal resistance is 0.6, 2.5 times 0.6. Oh no, 2.5 times 0.6. There. It's 1.5 dead on. Okay, so this is the only one theoretically, so I can't actually do any maths today, I do apologise. So this is the only one theoretically that could actually deliver 7.5 amps to a circuit and actually have an internal resistance of 0.6. It's the only one that's able to do it. You couldn't, if you had anything connected to the circuit, it would do nothing. Okay, but you would have a circuit that could fly. So the answer is D. And there we have it. There is a mixture of some of the nastiest electricity questions I could find, some very basic ones, and some hints and tips on how to do this. Hopefully this will help later on. And yeah, take care.